Okay, so here's a problem from the textbook, and it's an interesting problem, and it's a difficult problem to do. So let's just do it. So what's going on is that there's a skier that's taking off with some it's taking off at rest at the top of this hemispherical hill, and what's happening is that we have to figure out at the height from the top. We have to figure out this height h, okay, at which it is losing contact from the hill. Okay, so the question is, at what height below the top of the hill will the skier lose contact? So we have to figure out what this height is. Okay, so the problem is a little involved. So let's see how to go about doing this. So what we know is that the speed is it starts from rest, so we can figure out if it drops a height, this unknown height h, we can figure out the speed that the skier will have. Okay, so let's use MEI equals MEF to figure this out. First part is, let's figure out the speed. Okay, so once we know the speed, then we can draw a free body diagram for the object and then identify the forces. And for it to lose contact, what we know is that the contact force must be equal to 0. Okay, so MEI is equal to MEF, and at the top of the hill the skier has, let's assume the mass of the skier is m, has 0 kinetic but has some potential, which is mg times h. Okay, and this is equal, and we'll measure everything from the point that it's losing contact at, so that the final is simply the final kinetic energy and plus the height is 0. Okay, so V is equal to square root of 2g h. So now we know the speed. Let us draw the free body diagram for the skier at this location. So when the skier is here, okay, the forces acting on the skier are going to be mg pointing in this direction. We have the contact force pointing here, and as the skier is moving with some speed, we know that it has a speed of mv square over r pointing into towards the circle. Okay, so now if I choose my axis perpendicular and parallel with the acceleration, okay, we recognize that we need to break mg into components, and the component of mg along the acceleration, towards the center, is mg times let's just call this angle theta. So it is mg cosine theta, and the other component is mg sine theta. Okay, so where are we? So I'm calling this angle theta. Yeah. Okay, so if I have my diagram once again drawn here, this is theta pointing toward the center of the circle, which means this angle is theta. Great. So what we know is that mg cosine theta minus fn is equal to m over r times v square, and we found v to be 2gh the whole square. Okay, and now our condition is that fn has to be equal to 0. So we know that this has to be 0. So what we get is that mg cosine of theta is equal to 2mgh over r. Great. So now let's figure out what the height h is in terms of cosine theta, or what cosine theta is in terms of height h. And if you look at this picture, I'm just going to draw this stuff here. Okay, this is the angle theta, this is the arc, and what we know is, we know that this length is h. Okay, and if this is the radius r, then what we understand is that the length here is r minus h. So what we know is that cosine of theta is r minus h over r. Great. So we can now substitute for cosine theta, which is mg times r minus h over r is equal to 2mgh over r. Let's cancel out the mg's, and we have r minus h over r is equal to 2 times h over r. The r's cancel out. We have r is equal to 3h, and so h is equal to r divided by 3. So this is the height at which the object loses its contact.